Hello, physics students. This is the video that I promised, which you'd probably need for a couple of the problems in the assignment chapter 20, part 1. So note that this week we really focused on the magnetic field that was being produced by wires. So they could be short wires or long, like considering the wire to be infinitely long. Sorry, I'm trying to get myself out of the sun here. So those are two different things. So I thought first of all we'd start with one where the wire was uh, long. I guess those are the ones that we really wanted to focus on now. So the short wire wasn't a big deal, right? If you had, let's recall, what is the force of if you have like a shorter wire, then the force produced is equal to the current running in that short wire times the length of that short wire times the B field. And then if you remember, the other main equation that we're working with is for a very long wire, what is the B field? And the B field for a really long wire, if you remember, was that weird constant mu naught over like 2 pi, and then you had r being like the radius of the wire, the radius out from the wire wherever you were trying to measure from, and the current in the wire. Okay, so those are the two main equations we're working with. Of course, this one, if your current and your B field they were not perfectly perpendicular, remember this one had a sine of theta in it. Okay, so let's warm up with something fairly simple, I think. A little bit easier. So in this first example, you can see we have two wires. It looks like one is going into the page and the other is coming out of the page at us. And the question is for us to figure out the magnitude and direction of the field. So, in other words, what is B? And we're supposed to do so like right in between the wires, so at this location right here. Okay, so since one is going out of the page and one is going into the page, you can use the right-hand rule, not the left-hand rule. Remember, we have the two rules. So the right-hand rule, if you put your right hand over here and stick your thumb coming out like that, then you can see your fingers will curl in this direction and you're going to get the B field from that guy going up, right? Not bent, but straight up in a tangential fashion, just like we talked about all this week. If you curl your right hand over here and put your thumb into the page like it says, then your fingers are going to curl this way, and you can see that's also going up in a tangential fashion. So it looks like the fields are adding here. We did several problems like that in class, so should be a big deal. So all we need to do is calculate each field and add them up, and we should have what we need. So we do the first field using this guy, stick in our radius, looks like they said 5 centimeters, so 0.05 times 2 pi, put our mu naught constant in there, and our current flowing was 5 amps in each one, I believe. Oh, no, 5 amps is the one coming out, 7 amps is the one going in. So you're going to put 7 amps down here. It's also 5 centimeters away. So it looks like, of course, the 7 amps produces a little bit stronger field. So surprising, right? And we agreed that they were going to add up. So you get a stronger magnetic field than if just one of them had been there by itself. Okay. Let's do another warm-up kind of problem. So here's another conceptual example. This one has several different wires. So this would be very common to have wires like this in your house running to do different things, right? So it looks like we've got two going into the page. This one's going in, this one's going in, this one's coming out, and this one's coming out. That's supposed to be an X. And it says consider the field right in the center of that square configuration. So we're supposed to think about the field right here. And you could use the right-hand rule to check these little guys. Let's see, it just says in which configuration is the field greater at the center. So you can just use the right-hand rule to think about the field. That's what I would do. So this guy over here, if you stick your thumb out of the page, the field is curling this way, right? So that must be like this one. Okay, so let's do that. Let's do some different colors here to kind of keep track. Let's get rid of this. Should we use purple? I'm going to go for purple. Okay, so this guy, your fingers curl this way, so you have that little vector. This guy was going into the page, so stick your thumb in, and your fingers curl kind of like this, right? So I'm guessing that is one of these little guys. And then this one, put your thumb into the page and it curls like this. So that's going to be this guy, and I'm sure the other guy, if you do it, is going to produce this guy. So if you think about this, those fields, it looks like their Y components cancel, but their X components, assuming that they all carry the same current, it says equal currents right here, right? So assuming that they all have equal current, wouldn't the net B field at this point, the Y components would all cancel, and then you just have 4 times the X component of one of them? I think that would be the overall field in that case. In this case, if you check, I'm not going to check this time, but because of the directions of the current in and out of the page, they kind of switched them. Now you've got in here and out here and here. It looks like the Y and X components are going to completely cancel, so you'll have a negligible, if at all, magnetic field right there. Now that doesn't mean like you won't have one right here, or right here, or right here. You're probably going to have fields right there, but straight in the middle on this problem, you're going to have none. So of course the answer was that one. Okay, let's get into some new stuff now. And I'll probably split this into a couple videos for your digestion. Okay, so I think you also have several problems in your assignment that have 2 wires, and it asks about like the forces on those wires. So let's kind of develop the theory. Let's say we have 2 wires, the currents going the same direction, and they're separated by D. And let's just think about wire 1. So you can see wire 1 on the left. So let's think about its magnetic field. If you put your thumb up there, and you put your thumb going this way with the right hand rule, then you can curl your fingers, and your fingers are going to curl along here, right? And right over here, next to the second wire, you're going to have it going into the page, right? So let's fix that guy and make him an into the page symbol. Your fingers are going to curl into the page over here, right? And likewise over here. So at the location of the wire itself, you're also curling into the page, except instead of at this specific spot over here, it'd be a little bit stronger because it's closer, right? So the direction of the force, the B field is going to be into the page. The current's going like that. So let's use the left-hand rule, Fleming's left-hand rule, okay? So Fleming's left-hand rule, we're going to put our pointer finger into the page, and I encourage you to do this kind of up to your computer screen. Sorry, I can't demonstrate better. So you put your pointer finger into the page, then what do? With your left hand, so we're pointing into the page, then you curl your middle finger toward the current. So if I curl my middle finger toward the current, I think I'm going to have to point it up, right? So the force produced, I'll use green, my thumb is pointing to the left here, isn't it? So I think that first wire is going to exert an attractive force on the second wire. And I think if we apply the left-hand rule from the second wire to the first wire, we'll find the same kind of thing happens. So which way? I guess we could do that as well. Let's go down here on this one. So let's imagine curling our right hand around wire 2. So if we curl our right hand around wire 2, point our thumb up, then the magnetic field is going to be coming out at us at the location of the wire, right? So this is going to be an out at us field. Okay, so now let's go over there and use the left-hand rule. So over at this location, using the left-hand rule, put your left hand, try to point out at yourself. This is always that tough one. Then rotate until your finger is following the current and going up, right? So your middle finger should be up this way. Pointer finger should be pointing out at your face or something. It's hard to do. And you can see that if you do that, this one's always a tough one for me. But if you do that, your thumb should be pointing in this direction. So wire 2 is also trying to attract wire 1. So I think that what we found here is that if the currents in 2 wires are going the same direction, the force created, the repulsive force, is going to be attractive. Okay? So let's look down here. So if we have currents going in the same direction, we just proved that the force will be attractive. If the currents are going in opposite directions, we could prove that as well, but you could probably guess that their forces will be repelling. So how much is the force? I think we just need to go back and combine these two little equations right here. So let's just do that back on this page. So we said that the force, for instance, this guy was the one we were doing first, right? This repulsive force due to wire 1. So that repulsive force exerted by wire 1 on wire 2, I think that's our book's notation in case you're using it, is going to be IBL, right? So IB, which B field though? The B field produced by wire 1 and times its length, right? And we'd have a sine of theta on here, except I think that if we go back and look at our little diagram, since that one's going that way, like right into the page, and the current's going straight up, that's a 90-degree angle. So sine of 90 is 1. So we don't need to put our sine in there. Okay, so then I think we can put the B field expression in. So for wire 1, it's going to be I, and I should put, excuse me, I2 here. So I'm going to put the field for 1 is going to be, using that equation, mu naught over I1. This is the field being produced by the first guy, right? So then we have a 2 pi down here and the radius away. Didn't they call that d up here? Yeah, I think they called it d. So we'll call it d. It's not a diameter, right? It's usually like a radius away, but whatever. They called it d, so I'll call it d. And why is this I2? Remember, that's not, let's erase this and make it a little bit nicer. Remember, that's not like I divided by 2. That's current 2. Why is that current 2? I thought we were like thinking about wire 1. Well, let's remember here, the force on a wire is the current through it times the magnetic field that exists there due to whatever times the length of that wire. So this is like the length of wire 2 as well. Okay, so we're thinking about the force over here, this little purple force right here. So the current through wire 2 is right here. The field at that spot is due to wire 1, so that's right here. And then, of course, let's get this guy out of the way. We'd have times the length of wire 2 over here with the sine of 90 actually behind the scenes. So this is the formula that you can use if you have any problems where you have two wires interacting and it asks about the force. Okay, so that's what you can use. If you want to rearrange it and put like the I's next to each other and L up on top and all that good stuff, you certainly can, but I don't think you have to. Okay, so I will do one more video with like a couple more examples using this. So hope you watch that one as well. See you next time.